Welcome to Manifold. Apologies for the audio in today's episode. Corey and I are locked down in our homes because of the coronavirus. We're not in our usual studio, and so the audio may not be up to its usual standards, but I hope you enjoy the episode. Corey, our guest today is Raman Sundrum. He was educated at the University of Sydney in Australia and received his PhD from Yale University. He held postdoctoral positions at Berkeley, Harvard, Boston University, and briefly at Stanford. He was previously on the faculty of Johns Hopkins University, but is now at the University of Maryland, where he is a distinguished university professor. And he is perhaps best known for his work on a model for extra-dimensional space, which we'll get into, I think, later in the podcast. But what I'd like to do in our discussion today is start by just having Raman talk a little bit about his biography, his career trajectory, and then we'll get into the modern state of particle physics and where he thinks the field is going to go, say, in the next 30 years. So we'll first look back about 30 years, and then we'll look forward about 30 years. So Raman, we've known each other since the late 80s.
That's right.
And at that time, I was a grad student at Berkeley, and you were a postdoc.
Yeah.
And you, as I just read out your sort of career timeline, and so you had a number of postdocs, and it was quite a journey before you became a faculty member, even though everybody in the field knew that you were quite talented. And I just wanted you to reflect on what the job situation was like at the time, and has it gotten better? Do you think it impacts our ability to attract good people into physics?
I feel like it was definitely a very different time. It felt like the field was going in a very predictable way when I was a postdoc in the 90s. It just felt like I was out of sorts. I was questioning myself as I was not getting jobs and so on and so on. And I knew that I was somewhat outside the mainstream in terms of how I thought about physics and did physics. So I think I didn't really think of it as the job situation as being dire. I just took it as whatever was normal. Looking back, I kind of count sort of the same number of high quality jobs now as then. So I'm not seeing it in terms of job numbers that there's been a big change, but the type of hiring, who gets hired has changed a lot. The way the field views itself has changed a lot, and what it looks forward to has changed a lot.
Yeah, so maybe you could comment on those last few things, because I'm a bit out of it right now, being in an administrative job. So how is the field different than when, say, in the 90s or early 2000s?
Right.
And how is it different for young people?
Yeah. So one thing in the 90s, in the beginning of the 90s, there was still the possibility that America was going to have the grandest particle collider of all time, the superconducting super collider in Texas. And then beyond that, with slightly complementary abilities, was going to come the Large Hadron Collider at CERN in Switzerland. So we had this idea that a lot of particle physics, a lot of fundamental physics is going to be done in the lab, so to speak. Now, these were labs on a gargantuan scale, but we were looking forward to a lot of our ideas about theoretical physics playing out in these labs. And it was all ahead of us. So a lot of the work that the top theorists who are getting hired were doing were writing down theoretical models of what might be seen at these mega labs that were coming, these particle colliders. Of course, for various, political reasons, the superconducting super collider, or the SSC, was canceled in the 90s. So that ended up delaying the future confrontation with experiment into the 2000s. So when I was a postdoc in the 90s, a lot of the top jobs were, and a lot of the thinking was going into theoretical modeling. And a lot of the people that rose to the top in hiring were people who had the imagination to put the intersection of quantum mechanics and relativity, quantum field theory as it's known, into imagining what the physics just beyond our current understanding would look like, and then be tested at the Large Hadron Collider. Of course, a huge sea change has been that we've now been operating the Large Hadron Collider for the last 7, 8, well, about 8 years in earnest, and 9 years in earnest. And there has been one spectacular discovery, which was the discovery of the Higgs boson that many of your listeners would have heard of. But we have not gone beyond the standard model in what we've seen at the Large Hadron Collider directly. And so one big change has been that a lot of the thinking now has splintered from this one oracle that was going to tell us what was going on, called the Large Hadron Collider, to a myriad of other experiments that can give us information that might take us beyond the standard model of particle physics. There's, for example, dark matter. The evidence from astrophysics and cosmology tells us that there is something huge that is beyond the standard model of particle physics that we have very little idea about. So a lot of the thinking in the field has gone to, how do we mine dark matter in our experiments? How do we build better dark matter experiments than we used to do in the 90s? And these have flourished into a sort of many different aspects. And even theorists have been some of the most imaginative people in designing and imagining what kinds of dark matter physics and experiments to probe in the future. The cosmology has gone from great advances in the 90s to even greater advances now, and with even greater prospects for the future. So a lot of the theoretical thinking has also followed that and said, what can cosmological observations teach us? And people have also gone into thinking about particle colliders well beyond the capacity of the Large Hadron Collider, and hence what we might hope to learn on that front. But in a sense, while I had a lot of sense as a particle physicist in the 90s of having all my eggs in the LHC basket, experimentally speaking, now we see our eggs are distributed among a huge variety of experiments with almost equal probabilities for where, Nobel Prizes might be sitting. I think that's a big change, and it reflects itself in a lot of the variety. There's perhaps greater diversity of thinking, but it's become more focused. A lot of the even theorizing has become more focused on being a little bit agnostic about some big worldview of particle physics, and more opportunistic about experimental opportunities. Whereas my sense in the 90s was there was a lot more theorizing along, like, what is a particular paradigm that I find attractive? Is it supersymmetry? Is it technicolor? And trying to start from high principles and going close to experiments. Now it's like, what are the experimental opportunities? And we'll worry about the theory later. That's the biggest change in some sense that I've seen.
So getting back to the 90s, how should we feel about not a generation, but a decade or two of work where very imaginative models were built, but they all turned out to be wrong? So should there be any look back scorekeeping on whether the field was doing the right things in the 70s, 80s, and 90s? Or should we just say it is what it is? And, unfortunately, all these wonderful, beautiful Baroque models didn't turn out to describe TV scale physics.
So my feeling about the theorizing that took place in the 90s and even then in the 80s and the 70s is it's sometimes a little bit like when we're hiring a new faculty member or something, or thinking about writing letters of recommendation, where you look at somebody and you see that, yeah, they did a lot of dumb things and they've done a lot of great things. And how do I usually rank people or think about their value to the field? I value them on their best work, because all the junk that people do, right? The sheer inefficiency of human beings. The beauty of science is it cuts through that. It filters all of that out. But their best ideas stand the test of time, and are highly valuable. So indeed, when I look back on the theorizing that I would have done, or many of my colleagues in the 90s, and certainly before my time, and so to speak, in the 80s, I would say, so I'm about to justify to you why some of it was absolutely top-notch intellectual detective work and absolutely necessary. Mixed up in that was lots of second-rate theorizing and lots of stuff that could easily be thrown away. But we can only say that sort of with hindsight, which was which, because there's an innate inefficiency to science where we have to have a free market of ideas and we have to have a kind of adversarial system that eventually eliminates some of the bad ideas and keeps some of the good. So first of all, I don't want to justify the entire body of theory or entire body of detective work, even on the experimental front. But I do want to say that the best of it, and that's a lot, that the best of it was incredibly valuable, and in a certain sense that I will explain, is going to stand the test of time. And it's simple enough. If you're a detective, if we just put ourselves in the position of a detective, and he's got a whodunit that has to be resolved, what is the job of the detective? One is, please put out possible hypotheses as to, I think it's the butler. At least the butler had the opportunity. And then you have to say, well, what are the tests? How can we, if the butler did it, should his fingerprints be on the gun? And so we need ways of experimentally checking our hypothesis. And this is a cycle that we have to play over and over again. And we're not talking about your average whodunit, which are tough enough, okay? We're talking about some of the greatest whodunits in the history of the universe. So the level of pain and sweat and sorrow should be expected to be incredibly high. And we have to ask on that stage, which is, I want to say, kind of intellectually heroic, how do we judge what was done? And I want to say that the best work that was done in the 80s and 90s, some things that some people might look back and say, well, that failed, are some of the great hypotheses for who might have done it. And they were not just random, like, I don't like the look of the butler, I think he did it. No, they were the evidence brought to bear and the theorizing was exquisite in terms of why you might think it was this person or why it might be this plot playing out in nature. And the experimentalists have been part of that team in terms of, okay, so let's check for the thumbprints here in the cosmic microwave background. Let's check for the thumbprints in these experiments of the Large Hadron Collider. And to me, I look back at that era and I say that's the necessary process of science. The process of elimination of what is false is the pursuit of the true. To say that, oh, I discovered that some possibilities that were eminently plausible turned out to be false, that is a failure of science, is to completely misunderstand the process of science. So I guess in summary, I would say that I look back at those decades and I look at some of the theorizing that was done, and I am still agog in admiration, even knowing that some of the specifics have now been falsified. They were worth being falsified. Most things that come out of people's mouths might, at first sight, you say, look, it's not even worth my checking whether what you're saying is right. But these were worth checking, and it's part of the process that I think will ultimately lead humanity to great discoveries.
So my own view on this is that in many of these areas like supersymmetry or technicolor, there were beautiful ideas that got the ball rolling, and maybe the first 100 or maybe even the first 1,000 or top 100 or top 1,000 papers written in each category is very worthwhile, and future physicists will look back at these models. But then you have 10,000 papers that are, maybe should never have been written.
Indeed. I would agree with that in in hindsight. Although there, I would at least even ask you, there's a kind of a sociological problem of how to only keep those pearls of wisdom,
yes,
and not the other ones, in a free market of ideas.
yeah.
How would you organize it in some other way so that only pearls were ever produced?
Right. So we can talk. We can get into that because it's interesting to ask, like, would a different way of selecting talent or a different way of filling positions, have created a different set of papers written during those decades. But before we get into that, I want to say there's a big organizing principle that everybody at the time believed in called naturalness, right, or the hierarchy problem,
Yes.
which really motivated all of these models.
Yes.
And would you say even today we don't know, is the jury still out on whether we should believe in naturalness in fundamental physics? It's almost equivalent to asking whether the murder actually was committed, right? You're trying to find the butler, but someone might come along and say, no, the guy escaped. He's living in Bermuda. There was never any murder. This whole thing was a fake, right? So how do you feel about that?
So I have been wrestling with that for a long time, and one of the things that every scientist has to wrestle with is we're trying to know the truth, but sometimes some of us are hoping that our pet view of the world turns out to be the truth, and so it distorts our cold-blooded judgment. And usually, your cold-blooded judgment is far more accurate than your wishful thinking. So I have tried to set myself sternly by the hand and try to say, think this one out as carefully as you can. I'll summarize it by saying that I still come out on the side of saying I take the ideas of naturalness very seriously. Now, on the face of it, experiments have taken the ideas of naturalness, and naturalness is a kind of a gambling tool. It's a gambler's tool. It's just an extrapolation of how you would gamble if you went to Las Vegas. But it seems like what would have been the best gambles have not turned out to be correct. So something is up. So you can say, who loaded the dice, right? Something else is going on. And a number of ideas have come up, which I think are very interesting by their deceptive simplicity, like the anthropic principle, for how the dice could get loaded. And at the moment, my view is, I think I still put a lot of stock in naturalness. Not in some unloaded dice sense of the way of gambling, but the dice are loaded by something, by some other consideration. The dice are loaded, but you cannot give up gambling tools and in terms of gambling on what are the best bets for what experiments might see. So I have been pushing in many talks the idea of frustrated naturalness, that there's a natural sort of way of gambling when you know nothing, but clearly experiment has spoken already, and it says that something in the way we've been gambling is just wrong. So you have to look and say, what are the most, given quantum field theory, maybe not all your listeners will know that the grammar of quantum mechanics and relativity is incredibly tight. It's like the rules of chess. So the set of games of chess is infinite, and I think it's infinite, but it's incredibly a large number, and it's got great diversity. And yet there's a kind of like not anything goes in the game there. The game of chess is still highly constrained by its grammar. Relativity and quantum mechanics, the laws of nature are highly constrained by their grammar. Taking that into account, you have to ask how best to gamble on what's going on. I try to take that view as rationally as I can in every research project I do, in every talk I give in terms of where I tell people to place their bets. And I believe that naturalness is still playing, in my view, a huge role, but not exclusive role, in how I gamble. So in my view, the naturalist principle is alive and well. Scientifically, Sociologically, I recognize that many people feel like, oh, I tried using that gambling rule once and I got burned. And so I give up on it. I'm not one of them, but.
Yeah, I think.
Before we go a bit too far, can we, for our lay audience, give an explanation of the naturalness principle, the sense in which, I think some examples perhaps of how the laws of physics are constrained in their form. Give people an idea what is now thought to be the limited set of possibilities or structures of laws of physics, and what's out of the kind of out of bounds these days. So start with the naturalist principle. Most people who are not physicists aren't going to know what that is.
So one thing that we see in the laws of nature are simply that there are some very characteristic length scales. What do I mean by that? For example, if you are 2 meters high or 2 yards high, or you just have a meter stick in your hand, that is sort of a characteristic length scale for human activities and for human beings. We're all in the ballpark of this big. Yeah, I know some of us are this big, but we're all in the ballpark of about this big. So there's something about the human length scale that pervades a lot of our activities. Our cars are roughly human length scale, et cetera, et cetera. Now, if you look at the laws of physics, fundamental physics, you find that there are a variety of length scales. For example, the smallest conceivable black hole, before you would call it a black hole, the smallest that a black hole can be, is about 10 to the minus 33 centimeters. It's the length scale called the Planck length. So that's an incredibly, 10 to the minus 33 centimeters, or 10 to the minus 33 inches. That is an incredibly small length scale, but it's one that characterizes quantum gravity. The range of the force, the weak nuclear force that, for example, is responsible for radioactivity, the range of that force is, in fact, about 15 orders of magnitude bigger than the size of this characteristic smallest black hole. If we look through nature, the size of an atom is many orders of magnitude bigger than the range of the weak nuclear force. We find that there are some absolutely characteristic big picture length scales in nature, and like the size of the universe. So there's another one that seem to be spread out by orders and orders of magnitude. And in many ways, when we try to look from a theorist perspective, you're a theorist and you're making the laws of the universe. You're playing God a little bit. You find that in the presence of quantum mechanics and relativity, you find that when you try to write down the laws of nature, that the typical ones, if you throw darts at the parameter space of the laws of nature, that this very hierarchical structure that we actually see in experiment is very atypical. It's a tiny corner of parameter space in which something like that would happen. If you were throwing darts as God, throwing darts at the parameter space of the theory that we currently believe, you would not get that hierarchical structure. So the question is, what's going on? Throwing darts at the parameter space is like gambling. Where is the dart going to land? Well, it'll land in the typical spot on the dartboard. But we don't seem to be living in the typical place on the dartboard of the parameter space of the standard model theory. We seem to be in one which is a carefully chosen place in parameter space, which allows these huge hierarchies in nature to exist. That is the puzzle of the hierarchy problem. What's going on?
One of the things I've been thinking about since they discovered the Higgs boson and nothing else, and therefore we didn't find a solution to this so-called naturalness problem, is that maybe the probability measure over this parameter space that Raman was talking about isn't as straightforward as it looks to us. And maybe it's determined by some very short distance or high energy physics that will only become apparent to us when we, say, fully understand string theory or quantum gravity. And so maybe the resolution of this, maybe there is a resolution of this naturalness problem, but maybe it only becomes apparent when you really fully understand short distance physics.
So indeed, I think one of the nice developments in the last 10 years and 20 years and so on has been that people are rethinking naturalness. Some people sociologically speaking. Some people have just said, look, I have no clue. I abandon it completely. I become a kind of handmade into experimentalists, and that's great. So that's a reasonable attitude. I'm too dumb to know what's going on. That's okay. But other people have been playing with naturalness and trying to see in what sense it might still be not an idea that is completely wrong, but merely more nuanced than we originally thought. So, and the anthropic principle is definitely one of those ideas. It was originally brought up as a kind of, originally in its modern phase, since about 2000, has been brought up as a kind of replacement for naturalness. In my own thinking, and which pervades all my work, I would say, it is not a replacement, it is a refinement of naturalness. That is, I think both considerations become important. So one of the ways of thinking about it is, whatever the law, what we're doing is we're gambling on the laws of nature, because we want to know what experiment to do next that'll discover something interesting, something new. That means we're necessarily gambling on the laws of nature. We've seen some of the laws of nature, but we know for sure we haven't seen all of the laws of nature. In fact, in some sense, maybe we've only seen a small fraction of the laws of nature by some way of counting. So it's exciting. There's something to look for. How should we gamble on where to look? So when you're thinking about gambling on the laws of nature, one consideration, which seems like common sense after the fact, is whatever the laws of nature are, they have to be some way that allows intelligent life to exist in the universe. Otherwise, we wouldn't be sitting in the universe asking ourselves what the laws of nature are, right? So this sort of almost circular logic is true, of course, that if we're gambling on which universe and which set of laws we got stuck with in our universe, we should say, what does quantum mechanics and relativity allow in theory to be the laws of nature? Oh, there are many choices, many chess games are allowed. Well, which are the chess games that get played most often, are the easiest to play? We're probably in one of those, not in one of those exceptional chess games that hardly ever happens. This way of thinking about the laws of nature as to which are the easiest for quantum mechanics and relativity to put together has to be qualified by whatever the laws of nature are. They have to be the kind that allow life to exist, life like us to exist. So it is a kind of qualification of whatever you're going to gamble. Maybe if you are a theoretical physicist and you say, what are the most likely laws of nature that quantum mechanics and relativity allow? And then you say, this is the most likely one, so probably that's where you should gamble. You find that the universe that set of laws would create is a dead universe. It's one in which life could not even evolve. In that case, even though it's the most likely kind of universe to exist, you shouldn't expect to find yourself there because you're alive. This is the kind of qualifier that the anthropic principle puts in. It filters some of the gambling odds. It's like saying, I'm going to throw the dice. What number is going to come out? 1, 2, 3, 4, 5, 6. But let's say that every time you get a 6, you hide the result. You throw that dice away, okay? Obviously, it's going to change how you gamble on the other 5 numbers, right? The probabilities change. So this is the nature of the anthropic principle recently in a lot of the reflections on naturalness. It's a way of saying the dice are loaded. Another one that's come up quickly, that has come up recently, is the idea that in the measure, as you're saying, what are the odds, how are the dice loaded, is the other way of saying what is the measure of the probabilities, is considering cosmological evolution. A lot of the gambling about the laws of nature have often taken the place of a kind of static consideration. Here are the laws of nature, fully evolved. We know that from the early universe to now, in some sense, there's been some evolution in the laws of nature. There was a time when electromagnetism and the weak nuclear force were fused together into one mother force. And at some time, there was a so-called phase transition in the early universe where the two forces split off. In a sense, the universe has been splitting and evolving these forces. And that we should, in our gambling, we should take into account this dynamical process in how it changes the odds for what we're expecting to see in future experiments, is also being revised. Ideas like the relaxion have tried to play with this idea that cosmological evolution changes the probabilities that we would normally have thought about differently in the 90s, say.
I wanted to say, getting back to the first issue, first use of anthropic reasoning, which is just maybe how it influences the hierarchy between the weak energy scale and the Planck energy scale that you mentioned. Is there sensitivity? So the last time I looked at this, which was probably over a decade ago, there didn't seem to be that much sensitivity to, in terms of favorability to complex life on the weak scale. Has the thinking changed on that? Are there some mechanisms by which the weak scale, the strength of the weak interaction actually plays a role in the ability of life to evolve?
So within a kind of standard model of particle theory thinking, I don't know that much has changed in that 10 years that elapsed. In my own thinking, this idea of contemplating other possible laws of nature and whether they allow life is a tricky game, because you then have to say, did it have to be literally our kind of life, or could it be some other kind of intelligent life? And so it's a kind of uncertainty to which we are subject. Physicists love to think we're different from the biologists and everybody else because our subject is so sharply defined and a clean game of chess. It's too bad. It ain't. At the highest levels of ambition, every consideration comes back with full force and full uncertainty. So we are expected to not just be chess machines. Too bad. However, I have always maintained and still believe that if we try to imagine and calculate probabilities for life and other types of life too carefully, that we are liable to be making mistakes and compounding speculation on speculation, and I would not trust the conclusions. So I'm totally with where you were 10 years ago, and even where the state of the art was 10 years ago in thinking about what are the ingredients of life and so on. I would even push back on. But let me give you a different example, because I find it so both scientifically interesting and hitting this nerve of the anthropic principle and naturalness. So one of the great scientific questions is, we know that the laws of nature favor matter and antimatter hardly at all. In other words, antimatter is kind of our evil twin. And in the laws of nature, you can hardly tell the difference between matter and antimatter. They both look like they're sort of equivalent in some way. But amazingly, if you look at the universe, you find that it is full of almost exclusively matter, with very small trace amounts of antimatter. So one of the greatest scientific mysteries that's still going is, why is there so much more matter than antimatter? And it's a fantastic thing that the grammar of relativity and quantum mechanics allows us to write detailed models of the answer to that question. And it uses every trick in the chess playbook of relativity and quantum mechanics. And yet we have answers. We have possible answers to this question, why there's more matter than antimatter. Now, one of the examples of that, in fact, I consider one of the simplest examples of a theory of that sort, was one I wrote down with my colleague Janos Sui in 2013 or something. But it was built on the shoulders of supersymmetric theory, as an example. And she's written some follow-up papers on this since. Now, here's the thing. Supersymmetry was originally popularized, it wasn't invented for this purpose, but became very popular as a solution to the hierarchy problem, to understand why hierarchies of length scales could exist in nature naturally, robustly. So we built a supersymmetric theory which also explained why there's more matter than antimatter. And there's an amazing thing that happens in the parameter space. If you throw darts at the parameter space, you find that you end up with the most natural theory of the sort we wrote down, which naturally explains why the hierarchies of nature of length scales exist. But it turns out that in most of the parameter space, when you throw darts, you find that the amount of matter and antimatter is equal. In the beginning of the universe, all the matter and antimatter annihilate with each other and leaves nothing there, no matter left over. So this is a world in which all the length scales of nature are very natural. The naturalist problem is solved, but there's no bloody matter left over. So I don't have to talk about the architecture of intelligent life in great detail. There's nothing to make it out of in that universe. Okay, so the leaf has fallen in the forest, but there's nobody to see it. Now, it turns out that in one of Janu's models, where this is the case, that there is a slightly unnatural part of parameter space. That is, it's not the generic part of parameter space. It's not too small, but there's a smallish region of parameter space where if you happen to live there, our mechanism works and there's enough matter to exceed the amount of antimatter so that we see why there's matter in our universe. But now you see there's a tension. If this was the if the laws of nature took the form that is in that paper, and you lived in the generic part of parameter space, as gamblers would say, there wouldn't be any matter in the universe. If you live in this special corner, it looks less natural, but there's at least there's a chance that life could evolve and look around and say, why is the world the way it is? This is the nuanced view of naturalness that I am promoting. But it's not based on very fine details of why carbon plays such an important role in our kind of life, et cetera, et cetera. It's based on very crude considerations of the anthropic principle.
So Raman, I want to hop in a little bit, because Raman, I want to ask you about this again, because you probably did answer my question, whether it's mostly, whether we're detailed conceptions of life or kind of a broad sense that, look, you can't have life if there's no matter. You can't have life if everything is 100,000 degrees Kelvin all the time. When we think of the anthropic principle in most people's hands, is it any more constrained than simply these kind of basic boundary conditions, right? You can't have life if everything is gaseous, basically. Does it go beyond that generally, or is that the general way in which it's presented? Very, very basic constraints on simply complex objects existing of a certain kind.
So my own sense was that it was varied. People's views were varied. The famous Nobel Prize winner, Steven Weinberg, who, again, made the anthropic principle from kooky to mainstream, used a criterion for life as just being galaxies form. The end. Like, we at least got to have galaxies. You can't just have matter just strewn around, is dust everywhere. That seemed like a mild use of it. This idea that there has to be some matter in order to even have life, to me, seems like a very mild use of it. But it varied from person to person in a lot of the research. That's why I call it a marketplace of ideas, because different people can bet, no, I really think you've got to have the carbon atom. It's like, I don't even care if I go to some other planet on the other side of the galaxy, it's gonna involve carbon. Like, you might have different hunches, and each of us sort of has to ask whether we are willing to gamble all, which in my view is where to look for future experiments to pan out, right? We're hunting for gold, and I want to know where things are going to pan out. So how much are we willing to gamble that this conception of what it takes to create life is going to constrain where I look for new experiments to corroborate me? I think it varied from person to person. There were situations where I would not be willing to gamble because I thought that some of the considerations were too specific, and we may be at risk of our imagination of what life is being too constrained by what we've seen already. So the answer to your question is sort of it was all of the above. And I did not find it so fruitful in its most specific extremes of what it required of life. But the fact that anthropic considerations come into the universe we happen to find ourselves in, to me, this seems extremely likely. Whether we are able to figure out the rules of that by pure human thought is not obvious, but the fact that the anthropic principle is playing some role, I find incredibly plausible, as does a large fraction of the community.
So let me now express a skeptical question. And let me give you an analogy. We basically, as far as I understand, what you guys are trying to do, there's some question you ask about what the laws of physics are, but it seems like you're trying to ask a deeper question to why they are the way they are. And let me ask a skeptical question about that, possibly answering that question. So you roll a bunch of dice, it's as if you roll a bunch of dice and we find ourselves in a particular world where we see dice turned up on certain sides around us. Now you might say, okay, I want to know what probabilities led to this distribution. But it seems like you guys want to ask a more radical question, which is, why perhaps were the probabilities set the way they are, not merely what they are in our particular universe. And some might say, there's no way you can do that, right? You live in one world. You guys are trying to make inferences about what the distribution of possible worlds are. And how can you do that from this one single universe you live in? Maybe if you could travel outside of your own universe, you could do that. But how are you guys going to possibly solve this question, given that we have this set of, maybe there's some evolution over time, maybe there was some evidence that the probabilities have changed, and we can see history of that. But it seems like you're trying to ask about possibilities that you just simply don't have access to enough example distributions to infer.
I very much sympathize with that viewpoint and say, it may well be. We don't come with guarantees. That's absolutely for sure. So this way of thinking is only one way of us trying to gamble on what experiments to do and where to find new discoveries. It's one way. It does not come with guarantees. There is certainly a way of thinking when you only get to look once. You only get to look once, but you do many experiments, but you only get to pick one random one and look at what it is. There is a way of gambling as best you can in that situation, right? Let's choose anything. If you throw the dice and you get here's a dice in which if you get a 6, I give you a car, but we're only throwing it once. And here's another dice. If you get between 3, 4, 5, or 6, I give you a car. But we're only doing this once. But I'm going to give you a choice which game you want to play. But you only get to do it once. So yeah, the whole notion of probability is all about, well, you do it many times and probabilities become certainties. That's the axioms of probability theory. Well, we're only going to do this once, but I know which one you're going to choose. I know which experiment, which game you're willing to play, right? Because you're going to go and say, well, the probabilities are, I'll play the game where I get 3, 4, 5, and 6, and he gives me a new car. So we are gambling whether is there a guarantee that you're going to get the car? No.
I think what Corey's saying, though, is like, suppose you got the car, what can you conclude about which game you were playing? Were you playing a game where
exactly.
Only 6?
Yeah. And even there, you know that, yeah, you'd say, well, it was probably that. And if this game was only about, I think your car came from the 3, 4, 5, 6 game, and I think it probably didn't come from the one where you had to get a 6 to get the car, then you'd say, well, who cares? Who cares? I mean, I have no way of knowing. I can't play the game again. What am I to do? Unless there's something correlated with that decision, which you can go and test. Like if it's the 3, 4, 5, or 6 game, then when you open the glove box, you also have a diamond ring inside. You know, then you might sort of decide, well, that's a pretty good bet. I'm probably thinking it's the 3, 4, 5, or 6 one, and I know what to do next. We are looking for the next law of nature. We're trying to figure out, for example, what is the identity of dark matter, or how did the Higgs mechanism truly work? We have something to gain in the future, and we're trying to see whether our gambling tells us what are the best places to look, or what should we give up on? If the LHC did not see something beyond the standard model to date, it may tomorrow, maybe we should stop running the LHC, right? That's a question we could ask. Is it a good gamble to stop running the LHC? That's a once in a lifetime decision. You don't get to do that 1,000 times. But you have to use probabilistic thinking, as we do in everyday life, to make that judgment call. Is it worth doing that? So this thinking comes up even when you don't repeat it many times to make probabilities into certainties. But I would argue that we use that kind of thinking in ordinary life. This is not some strange, weird philosophy by some desperate particle theorists. This is an extension of ordinary thinking about ordinary once-in-a-lifetime decisions, or twice-in-a-lifetime decisions.
You know, Corey, I'd like to make the comment that, you know, the vast majority of physicists are experimentalists, and they're working on gathering data, pinning down the laws of nature, et cetera, et cetera. Then you have the smaller community that are thinking very complicated thoughts about, oh, what's next? Why are the laws the way they are? Do we have any inkling of why that might be? And so in a way, this isn't the primary necessarily activity, at least in terms of head count of or dollars expended of what physicists are doing. But it is important because sometimes some insight will come from that small theoretical community, and that will actually inform the next $10 billion machine or dark matter experiment that people do. And maybe you'll get to the answer faster because of some of the insights from this small community. But if you think of it as this small community is the whole thing, then I can forgive you for thinking like these guys are like philosophers, you know, arguing about how many angels can dance on the head of a pin. It can seem that way, but in the past it has paid off to have a community like this reasoning this way.
I would actually greatly agree with what Steve just said, because in some sense, this way of gambling on the laws of nature, well, we have gambled in the past in various different ways. We've gambled with some aesthetic sense on what the laws of nature are, and people have made their gambles. And of course, the best of those have actually survived and have become the laws of nature in the modern era. So this idea of having to speculate a little bit theoretically and then checking and looking experimentally is a time-honored tradition. There can be bad versions of it or good versions of it or lucky versions of it, but it is a time-honored way of doing science. And so the details, that's what I think even I said, this is one of the ways we are gambling on which experiments to do. One thing that Steve is hinting at also, which is definitely true, is that this way of thinking, of gambling on it by thinking about what's the typical universe, the typical laws of nature, and so on, the ideas it's brought up in terms of which experiments to pursue, again and again, even when you erase all the philosophy and you say, just as an experimentalist, is that a good experiment to do? Again and again, you are struck by the fact, wow, I did not independently think to do that experiment. But now that I look at it, what a stunning way of probing nature. So orthogonal to everything that's gone before. So for example, thinking about supersymmetry, invoked often as a solution to naturalness, and the anthropic principle, in some set of considerations, led to an idea called split supersymmetry, in which a certain kind of new particle could emerge that could be producible at a collider, and it would have a very distinct behavior, it would leave a very distinct kind of track and hits in the detector than the kind of things that people were looking for prior to that. Remember, nobody tells the experimentalists they have to listen to any of this philosophy. They can do whatever they want with their experiments. But they hadn't conceived of looking for this kind of particle, this highly stable charged particle. All of a sudden, they were like, wait, I don't even follow your philosophy, but that's a damn good idea for an experiment. So whatever you consider this kind of, as Steve pointed out, sort of angel dancing on the head of a pin aspect of the subject, it produces the goods in the sense that it produces places to look experimentally, which often direct agnostic thinking about where to look does not bring up. But then when somebody tells you, hey, have you ever thought to look in this direction? I may be completely certifiably insane, but I think you should look in this direction. And then you think, yeah, you are insane, but that's a good idea. And you go, look, I feel like again and again, the subject has had that feel to it.
So I want to take a step back from the slightly philosophical bent here and ask some concrete questions. Like, so you mentioned dark matter, and we haven't discussed dark energy at all, but I'm curious, how surprised will you be if, say, 30 years from now, let's say we have about 30 years of life left in us, maybe not high-functioning life, but we have about 30 years of life left.
Mine is high-functioning life. Steve, I've not become an administrator yet.
Okay, good. I meant like as you get old, you get dumber, and you can't walk and things like that.
Speak for yourself.
Okay. So let's say you got 30 years-ish, maybe for you it's 50 left. What are the odds that at the end we're not going to have found the dark matter, the actual particle nature of or whatever the nature is of the dark matter? And similar question for dark energy.
So before you guys hop in, can you define each of them and distinguish them?
Yeah. Dark energy is basically the statement that we're observing. So the observational basis is we are observing that our universe, which everybody knows that we live in an expanding universe, but for the last 20 odd years, we have seen evidence that our universe is not only expanding, the rate of expansion is increasing. In other words, we're living in an accelerating universe. Now, why that stands out is that in Einstein's theory of general relativity, which governs gravity, and in particular governs the gravitational effects that dominate the universe on the largest scales, there is a connection between the expansion rate of the universe, how the universe expands, and what the contents of the universe are. The contents of the universe dictate how space-time stretches and expands. Now, it turns out that most of the contents that we can imagine the universe is made of, like you and me, are forms of matter. There's radiation, like the light flooding in to the window. Most of the stuff the universe is made of, matter and radiation, it allows the universe to expand. It's consistent with the expansion of the universe, but it's not consistent with the universe accelerating. It would normally only be consistent with the universe decelerating. So there's something singular that has to be in the universe to allow it to be accelerating as we see it to be, okay? And in cosmic history, the way that Steve and I are trained to think about it, this switch, the universe has only been accelerating relatively recently in some way of thinking about cosmic time. And so the question is, what is this magical substance that's in the universe that makes the universe accelerate in its expansion rather than decelerate in its expansion? The name given to it, if you're a complete agnostic, it's just the name for whatever this hypothetical X is dark energy. And the most obvious theory for it is Einstein's famous cosmological constant term in his Einstein equations of general relativity. but maybe it's something more subtle than what Einstein had originally conceived as the cosmological constant. So because we don't know for sure experimentally, we just call it dark energy. And so that's what that is. It's pointing to something that's accelerating the expansion of the universe, and it's not regular stuff like matter and radiation. On the other hand, we also have evidence that the galaxies that we see with our eyes in terms of stars made of atoms are really, they have a dancing partner which we cannot see and is far more massive in the form of dark matter. So for example, the usual spiral galaxy that we imagine a galaxy to look like secretly has a ball of dark matter surrounding it. And how do we know that? Because, well, we know it from a variety of ways, but one is the way the stars are moving, the stars that we can see, the way they're moving does not follow from the usual laws of Newtonian laws of gravity, or even Einstein's refinement of the laws of gravity. They don't work according to the laws of gravity that we have tested. Unless there is secretly some invisible matter which is adding to the gravitational force that these stars feel. So this sort of invisible person pulling on us, this invisible stuff that's pulling on the ordinary stars, is given a name in honor of its mystery, dark matter. We see the dark matter, sometimes dark matter is like a ghost. If you ever see a ghost in a movie, sometimes you can't see the ghost. But when the ghost walks by, the background ripples a little bit, just in honor of trying to show that there's a ghost walking by. We literally see that kind of distortion of the background from the presence of a ghost. When we look at very distant collections of galaxies, which are made of ordinary atoms that we can see, we sometimes see a distortion of the picture where the galaxies sort of get distorted into these arc-like distortions, as if there's a ghost in front between our eyes and those distant galaxies. And there is a ghost in front. It's dark matter. And it's bending light, just like ghosts do in the movies. It's distorting the light rays coming to us. So we have a number of different ways from cosmology and astrophysics of seeing that we're not alone. When I say we, everything that's made of the laws that we understand, atoms, electrons, quarks, gluons, all of that, we're not alone. And in fact, we're outweighed 5-1 by whatever this mysterious dark matter is. So that's dark matter. But the distinction between dark matter and dark energy is dark matter by itself would still, it's magical stuff, but it would still not allow the universe to accelerate in its expansion. On top of dark matter, there has to be some other X, which is dark energy, that allows the universe to not only expand, but accelerate. So that's the distinction I'm making between those two, or the world makes between those two.
So back to the original question, what are our odds of discovering the true nature of the dark matter and also the dark energy, say in the next 30 to 50 years?
So I guess my answer would be slightly different for both of them. My hunch is that so first let me make the relative statement. We're much more likely to discover the nature of dark matter. We know something about it, it's there. We feel its gravitational effects, but to know what it's really made of, are there little creatures living inside dark matter, made out of dark matter particles? All of that kind of thing. I think it's much more likely that we find out the answer to that exciting question in the next 30 years than it is that we find out what underlies dark energy. Nevertheless, it's possible in an optimistic take that we find out something very significant about both of them. But I would put more money on the nature of dark matter than I do on our ability to discover the nature of dark energy. In terms of absolute probabilities, what do I think the odds are that we would even make great progress on dark matter? 10%. And you may say, or an ordinary person might say, you're not very hopeful. And I would say, no, I'm a fundamental physicist. I'm wildly optimistic. And that's why I'm calling it 10%. Because we are talking about mysteries which are not like, you know, will the yen go up tomorrow or not? No, we're talking about some of the deepest mysteries that humans have no right to know the answer to. So to say you have a 10% crack at that is enormous.
Now, would you say, wouldn't you agree that your 10% though is low compared to, say, the community of astroparticle physicists? They seem much more confident that 30 years to them would seem like their entire career, maybe, that they feel pretty confident they're going to find something. Is that fair?
I think that when you wake up in the morning and decide to go for it, there's always two halves of you. I don't know that I'm that different from everybody else, but there are two halves of you, only one of who's answered your question. The two halves are sort of like you're trying your best to keep a level of indifference. I don't care whether they find it. I don't care if they don't. I'm just answering your question neutrally. But at some point, you know, every day you pull your socks up and then you say, I'm going to go and battle the world. I'm going to make that discovery happen. And of course, the truth there is, if it is humanly possible, I'm going to do my damnedest as a theorist or an experimentalist to make sure that we see it. But there are some things that are beyond human control or ingenuity, and we can imagine the kinds of situations where in 30 years we will still not be able to pull this off. So when I put all of that together, and I speak very neutrally and unemotionally, this is about as unemotional as I get, by the way. When I do that, I say, yeah, you know, it's 10%. But to me, 10% at getting that kind of mystery resolved is huge. And the set of experiments we'll do, it's what one of my colleagues is in the community has called like a high quality no. Even if you don't get the answer, but you do this enormous array of experiments, each of which is trying to do the impossible, bring this ghost to life. If you have a 10% shot at that, it's super exciting. And even if you don't succeed, but you do these incredible experiments, that's what they were calling a high quality no. You have ruled out something brilliantly well, and that leaves other possibilities open to pursue for the next 30 years.
I feel that one of the things that's not appreciated so much in other areas of science is the idea of setting limits. So even if you don't find, you have, say, a direct detection experiment for dark matter, you don't find the signal that you were hoping to find, you're at least putting a limit on the properties of the dark matter. Otherwise, you would have seen the signal. And in physics, we value that not maybe as much as the discovery, but we certainly value it in a very non-trivial way. You could make a whole career by setting really beautiful, strong limits on things. But I find in other fields, I'm always shocked to meet another scientist, say a neuroscientist, and you say, well, what's the upper bound on the rate of neurogenesis in an adult? How many neurons can I expect to grow next week? They have no idea. They don't even think that way. So that I find very different in the way that physicists think versus other scientists.
Indeed, if you just put yourself in the position of a murder detective or something, to be able to say with super high confidence, the butler did not do it.
Exactly.
I can rule that person off. I've been at this for 40 years. This is a cold case. I've been at it for 40 years. And I now have discovered something super important. I'm so excited. The butler did not do it. That's incredible for this detective that's been going 40 years to know for sure. Now, that doesn't tell him who did do it. Could be somebody else, this, that, the other. There's work to be done. But this is a high quality, if you never were quite sure, then you'd always be circling back to the butler. Maybe it was the butler, you know. But if you think you've done this absolutely top-notch job of ruling out the butler, you've done every experiment on the butler possible, even that is a great act of science. And that's why I don't want that to be called a failure. Because I do have faith, even though I have no scientific reason to say it, that over the long haul, which goes beyond my life, I think that, yeah, I do think that humans, if we survive, I think that humans will find out what is the nature of dark matter. There, I've said something even hopelessly optimistic. But I believe it to be true. I believe it to be true because I'm constantly amazed by what the human is capable of doing.
Steve, I think this is also just a difference in physics. To some extent, you guys are very lucky because you have fairly simple systems and the probability distributions are pretty well understood on the base. You just know how much systems are going to vary. I think it's a very important question for neuroscientists and others to ask. But I really wonder how precise your confidence intervals would be, given that you actually don't know much about how organisms vary when you get to such a complex level.
I'm totally okay with people saying we don't have the experimental tools to get a decent bound. I thought really hard about it. The uncertainty is enormous. I like that answer. That's a good answer. The answer I don't like is like upper bound. Why do you care about that?
Yeah, of course. I think that's a deficit. Yeah, absolutely.
Yeah.
But maybe a deficit born of just a lack of experience with things where you got comprehensible answers on. People stop. The question just never became part of the culture as a result.
Right, exactly. But what's funny is that as they get better and better tools and technologies, what was absent for good reasons is now absent, even though there's actually money to be made by trying to address those questions, if you see what I'm saying. Like what wasn't possible for a long time can suddenly become possible, but they're not used to thinking that way.
Yeah, indeed, I do think that there is some sort of like the proper take on our field requires understanding the level of its ambitions, the range of experiments and probes that we are doing, their richness. Even as an outsider, I think that can be understood. Like what we are daring to ask, like, why is there matter? What a question. It sounds like it's the kind of question only a lunatic would ask. But the fact that we can write detailed theories that then require experimental checks for answers to that, I think once you appreciate that level of ambition, I think you become more forgiving. Not forgiving about crappy second-rate papers, but forgiving of the highest level of work, which sometimes temporarily at least ends in failure. Oh, the butler did not do it. But is secretly the stepping stones to ultimate success. But the grandeur of these questions is worthy of more than one generation. That's my take. And I think once we accept it and proclaim it to ordinary people, I think they will accept that some part of the portfolio of human activities, somewhere on the fringe, there should be these guys pursuing this level of extreme activity. I think it can be explained and it can be understood by ordinary people, and it should.
I think for the man in the street or even the professor out on the quad, what you just said is entirely reasonable, and they would say, "Oh yeah, absolutely, civilization should have a group of people pursuing these questions." The problem is when you get into the level of the bureaucrats that are allocating national budgets. And someone says, "Oh, I'm going to have a cure for cancer for you," or "I'm going to have a vaccine for COVID-19." That can suck all the energy, all the money away from some field that says, "Well, we're doing really hard stuff. It's going to take us 50 years to make progress on this, but keep funding us." That's the battle which I feel, at least in my career as a physicist, we've been kind of losing. So if you look at our share of natural research R&D budget, it has not been going up, and we didn't get our super collider, for example. That was the big tragedy of our young lives in some sense.
Right.
Yeah, and so we're kind of slowly losing a battle here. And so I don't like that. The other comment I wanted to make is that I feel that, just speaking personally, I was rather spoiled because I came into the field when this sort of quantum field theory revolution had happened, and gauge theories, and all kinds of huge progress had been made. And so you get spoiled by that. So you think, oh, this is the normal pace of discovery. Oh, in another 5 years, they'll finish the SSC and we'll have the Higgs boson and maybe a bunch of technopions or something.
Right.
But then you don't get that. And For me, the issue was that I could see other areas of science where the technology was at a propitious place to re-experience that feeling of riding on the motorcycle at 200 miles an hour that maybe some older physicists got to experience, but I would say, didn't get to experience. But now in some other fields like genomics or AI or internet-related stuff, there is that kind of, excitement and pace of change. However, the questions they're addressing are not quite as fundamental in my mind as what say you're working on.
So I think I agree with all the sentiments, which are sort of partly just, this is the emotional take that anybody who lived through what we've lived through would feel. And in a sense, it's often when we're trying to sort of understand the situation we're in, we're looking for some precedent for how to think about it, how to label it. And in some ways, what's happened is rather unprecedented, because the discovery of quantum mechanics and relativity under finding them under very humble rocks, like a little bit of radioactivity, a little bit of static electricity and magnetism.
Two slits.
Yeah, exactly. And then suddenly, it's like the fire hydrant of fundamental physics is pouring out of the beginning of the 20th century. And it's like, it's both super fundamental, it rocks your entire worldview, all your philosophies have to change, and it's cheap. It's just pouring out at a high rate. That very abundance has pushed us to where we are in our understanding now, which is incredibly high compared to 150 years ago. And we are victims of our success because we have climbed incredible mountains as a species, and we know that we are still only at the foothills of our understanding. And we say, why not go higher? We're humans. But what is technically feasible has not kept pace at quite that rate. So we know the grand questions await us, and yet we find ourselves as ants compared to where we want to be in terms of our strength. And we don't know what to do. We don't have a situation which has a precedent like that. In the past, it was just like we were one idea away from immense power to do a whole new range of things. And truly, we may be again, we may again be victims of thinking, oh, look, I have a simple way of checking quick orders of magnitude estimates to tell me why life is really hard as a fundamental physicist. And it may be in 30 years, we're laughing at that, playing this podcast or whatever. And we're like, gosh, they were so hopelessly blind because they never saw this thing coming from left field. So I feel like, yeah, I get the sentiment. The real question is, with all of these other things going, one, COVID-19, okay, cancer research, pandemics, all of these things. And then other things which are on their ground floors still, like machine learning or something like that. Why do we have to go back to this ancient business of fundamental physics? Why do we have to keep putting money in it? And I would say, look, it's an unprecedented situation. If you're looking for some good old history lesson to tell you why you should do it, you're out of luck. We're going to have to use our own judgment. And I would say, in the portfolio of human activities, this occupies a relatively tiny fraction of our efforts. The people who do it, the best of them, have been incredibly creative. Even if and the spin-offs from it have been a little bit like what I said about experimental spin-offs from thinking about the naturalness problem. The spin-offs have been all sorts of practical things. They have, in order to do the experiments, they push materials research like crazy. They push atomic physics like crazy, quantum physics like crazy, machine learning like crazy. So just to do whatever it is these crazy fundamental physicists do pushes the art of everything else in a way that may not get pushed by itself. And these guys are really smart. They're really imaginative. They may be crazy, but they're imaginative. So is it good to have that sort of jester in the court? Yeah, it's good. How much should we have of them? tough call, subject for another podcast. But should we? Yes, and we should not only have them, we should not just tolerate them. We should celebrate them, I think. And look at the questions they're going for. Yes, while we're worried about COVID-19, I'm still worried, where did all the matter come from? That's the beauty of humans, right? So I would celebrate it rather than for some political short gain, try to set these at odds with each other. In that sense, we're utterly vulnerable. Anybody can attack us and sound pretty plausible doing it. I think they're wrong. And if you hold them still long enough to debate it, they will be seen to be wrong. The other point that I have made in meetings with serious people is that you never know with fundamental physics. You never know. I am dabbling with wormholes in my research. You never know what crazy thing is going to happen. As one physicist said, I don't know how likely any of these things are, but if anything like all the things you're watching on Star Trek are ever going to happen, and maybe it's long odds that they are, but if they are going to happen, it's going to happen by this kind of research. So that's how I answer that.
Without setting out to do it, I feel like you've given a good response to our earlier podcast with Sabine. And so maybe we should stop there because we've had you now for almost 90 minutes and we should probably let you go. But that's a great place to cap it off.
Very good. It's a pleasure to be here.
Yes. Well, we'll have to have you back.
Sure. That'd be fun.
Take care. Hey, before I let you go, so how's the family? Your daughter, how old are you have two daughters? Or
I have
one
two
daughter?
daughters, yeah.
Two daughters.
I forget whether the other one was there when you had visited, but she probably was, yeah. Anyway, I have
Yep.
two daughters.
Yep.
One is about to finish high school and she's going to do engineering at Carnegie Mellon. And the other is in 7th grade.
Oh, wow. So she's pretty young. Yeah. Well, our kids are in they're in 9th grade. We have a boy and a girl, twins.
Twins. Okay, great.
Yeah.
So that's the beginning of high school. So
yeah.
Was that an adjustment or they were just fine?
Oh, it was a huge adjustment, actually.
Yeah.
I'm a super high investment parent. So this last few weeks with the lockdown have been hugely stressful, not because of even though we have all this crisis management stuff we're doing at the university, but mainly stressful because I got stuck doing homeschooling with my kids because their school didn't really pick up right away. Now they're going to start next week, but we weren't sure what their school was going to do. So we were just on our own for 3 or 4 weeks, teaching them. So that takes a lot of time. It's after I finish something like one of these video meetings, I have to run over there and see what my kid is doing with his calculus or something. So
I had exactly the same experience as you, and I'm in exactly the same position. With one difference, my kids fired me.
I didn't let them fire me.
Yeah,
I refused to fire.
I'm a weakling. I'm a weakling, and so I don't know how to reinsert myself into I had this whole program of look, I'll teach you stuff. It's even better than doing your classwork. Yeah. And they show absolutely zero interest in anything I'm saying. So I've been fired, and hence I have time to talk to you.
Oh, that's great. Yep. All right. Take care.
Okay, then.
I hope to see you in person soon.
Yeah,
Okay.
absolutely.
Okay.